Okay, let's jump right into this explainer. Today we're doing something really cool. We're literally pitting three distinct artificial intelligence paradigms against each other in a massive, highly complex digital arena. It's the ultimate showdown of reasoning, visual perception, and raw efficiency, all to see who rules the bleeding edge of scientific visualization. Just look at this. When we say scientific visualization, this is exactly the kind of mind-blowing stuff we're talking about. It's the absolute art and science of taking raw, staggeringly complex, high-dimensional data and turning it into visual reality. We're talking about rendering massive supernovas, tracking microscopic argon bubbles, modeling the insane fluid dynamics of a tornado. It basically bridges the gap between pure abstract math and human comprehension. But here's the catch. To do this, researchers have to use incredibly intense, highly specialized software like ParaView. And the crucial point to understand here is that SciViz is notoriously hard for humans to use. I mean, it requires a really deep understanding of rendering pipelines, super precise filter semantics, and complex coding APIs. Researchers are out there spending hundreds of hours just wrestling with these interfaces instead of, actually analyzing their data. Because of this massive learning curve, scientists are asking a pretty bold question. What if autonomous AI agents could just take the wheel for us? Could an AI actually navigate this insanely complex software and build these visualizations from scratch just by reading a simple natural language prompt? So let's move right to the starting line. Part 1. Meet the contenders, the three paradigms of AI. To really test these architectures, researchers set up a showdown to figure out which type of AI is actually best suited for these brutal, multi-step digital tasks. We can kind of think of our competitors as three very distinct types of workers. First up, the specialist. These are your domain-specific agents operating on really strict, pre-programmed APIs. They're fast, highly efficient, rule-following machines, but they totally lack flexibility when you throw them a curveball. Next, we have the intern. These are computer-use GUI agents. They literally look at the screen and click around the interface exactly like a human would. They have visual awareness, sure, but they get easily lost. And finally, the brute force coder. These are general-purpose coding agents operating straight from the command line. They write highly complex scripts completely from scratch to basically just hammer the job until it's done. Which brings us to part 2, the ultimate AI showdown. So researchers put these three paradigms through the ringer, 15 brutal multi-step SciViz tasks inside the ParaView software. And wow, the data reveals a staggering contrast. Our brute force coder, represented here by Codex CLI, absolutely crushed it with a flawless 100% completion rate. But look at the cost. It burned through over 774,000 input tokens per task. To put that into perspective, running that many tokens repeatedly is going to rack up absolutely massive cloud computing bills. It's a hugely expensive way to get a result. Compare that to the domain-specific specialist, chatgpt. It completed 45% of the tasks, which is lower, yeah, but it used a mere 8,000 tokens. That is a radically different and way more economical approach to problem solving. Now, if you look at the Pasek curves right here, you'll see exactly how those general-purpose coders actually pulled off that win. Spoiler alert, they didn't just get it right on the first try. Nope. They essentially brute forced their way to success over repeated, highly costly trial and error attempts. It's like this. They write the code, it fails, they read the error, they write more code, and they just keep pushing and pushing until the visualization finally works. It's wildly effective, absolutely, but incredibly computationally expensive. So when we stack up the brute force coder against the specialist, we are looking at a massive trade-off. It's the sheer unyielding capability of autonomous code generation on one side versus the elegant, low-cost efficiency of constrained API use on the other. Bottom line, if you want an absolute 100% guarantee that the job gets done, you are going to pay a massive token tax. But if you want lean efficiency, well, you're going to have to sacrifice some of that flexibility and completeness. Moving right along to part 3, the GUI planning problem. But wait, what about our intern? The GUI-based agent that interacts visually? The one that's supposed to navigate the software interface just like you and I do. Honestly, you really have to wonder why an AI that can actually see the interface, read the menus, and move the mouse around failed the vast majority of the time, clocking in at an abysmal 27% completion rate. Like, what's going on there? Is its computer vision just failing? Is the AI just getting completely lost among all the buttons and drop-down menus on the screen? To figure out exactly where the disconnect was happening, the researchers designed a really clever, stepwise evaluation. They approached this almost like a mystery. They took these incredibly long visualization tasks and broke them all down into 5 isolated steps. Then they reset the environment to a perfect, gold standard state before asking the GUI agent to perform just one single isolated action. Basically, they held the agent's hand to test its true visual capabilities, totally free from the baggage of any past mistakes. And the data reveals a major twist. Just look at this massive jump. Their success rate rocketed all the way up to 64% when the tasks were isolated. This proves a huge point. The GUI agents didn't fail because they couldn't see the interface, and they didn't fail because they couldn't understand the buttons. They failed at long horizon planning. When forced to execute a complex sequence of actions over time, completely on their own, they just fell apart. So compounding errors are the real enemy here. Imagine you're rendering a super complex 3D supernova. If our intern makes just one bad click early on, maybe say selecting the wrong data filter, it ruins the entire visualization pipeline down the line. It's kind of like having a coworker who makes a tiny math error on page 1 and doesn't even realize they've messed up the entire project until the final report is printed out and the image on the screen is complete garbage. All right, let's get into part 4, the advantage of memory. So if these compounding errors, long horizon planning issues, and repeated brute force failures are totally bogging down our AI agents, how do we fix it? How do we build an AI that actually learns from its time in the software? Well, let's take a look at the number 30.78. This was a specific score achieved by a general-purpose agent framework called LEDA. And this number is important because it represents a massive leap in capability that gives us a major clue about the future of autonomous digital workers. You see, when persistent memory was enabled, LEDA's baseline score shot up from 19.09 to 30.78. By giving the AI a literal memory of its past sessions, it actually learned from its previous mistakes. It's exactly like an intern taking detailed notes instead of making the same exact mistake twice. Instead of exploring the same dead ends and writing the same broken code over and over, the agent remembered what failed in the past. This drastically cut down on computational waste and massively boosted its efficiency over time. Which perfectly tees up Part 5, Building a Hybrid Future. This brings us to the resolution of our great AI race. And after analyzing the specialist, the brute force coder, and the visual intern, the truth the researchers uncovered is that there is no single winner. Each paradigm has a fatal flaw when operating totally alone. So the future of scientific visualization relies on building a hybrid, almost Voltron-style agent. Imagine combining them all, taking the specialist's rigid efficiency for the basic tasks, utilizing the coder's brilliant reasoning for complex workflow generation, employing the intern's visual GUI grounding so the AI can actually verify if that supernova looks correct on the screen, and then tying it all together with the adaptable power of persistent memory. As we wrap up this explainer today, I really want to leave you to ponder this. Right now, AI is still just learning how to accurately verify what it sees on a screen and plan 10 steps ahead without stumbling over its own shoelaces. But once a hybrid AI truly masters visual validation and long horizon planning, seamlessly navigating complex software just by looking at it, what highly complex human tasks will it conquer next?